Welcome to today's session on machine learning or data science classification techniques. In this session, we are going to look into a number of classification techniques in machine learning. We start with a little bit of introduction to machine learning. Some of you have probably got idea about what machine learning is, but maybe not all of you have got a fair idea about what machine learning is. So we start with a bit of use case understanding and understanding of what is machine learning in a broad sense. So machine learning is the study of computer algorithms that improve automatically through experience and by use of data. It is seen as part of the artificial intelligence. Machine learning algorithms build a model based on sample data known as training data in order to make predictions or decisions. So what does it mean? That means is that machine learnings use algorithms, they create models, and the algorithms go through a process called learning, which is from the data that we feed it. Okay, we will look into it a little more in detail with a basically comparison between traditional programming and machine learning in a bit in the next slide. But before that, let us understand with some examples as to what are the different use cases of machine learning. So we have voice assistant. So let's say, for instance, I give this example quite often. You want to book a restaurant. All right, so you call up the restaurant help desk and my help desk number, and somebody picks up and you say that, okay, I want a booking for 4 persons at your restaurant at 8 o'clock in the evening. Okay, so the person on the other side takes down your phone number, your name, and etc., your details, and makes the booking and confirms to you on the phone that your booking is confirmed, sir or ma'am. Right. So now, little did you understand that the person on the other side was not a real person. It was a human. It was a machine assistant. So what happens at the background is that there are multiple things in play, right? And they use machine learning. So the first one understands that there is a voice to text converter that is working, and the second is so that converter takes in voice inputs or sound inputs from your phone call and converting them into equivalent text. So essentially, that is a machine learning algorithm which has been trained on loads and loads of data, which is voice data, and it has been given that, okay, if this is the voice, this is the corresponding text that you have to convert to. So it has been trained on loads and loads of millions and millions of sound bytes and corresponding text levels, right? So that is one thing that is at play at the background for the voice assistant. The second part that is in play is probably a little more complex, which is conversation. So the way you are talking is different than somebody else will be talking on the phone, and every single conversation, even if the aim is same, will be slightly different, right? It is almost impossible for somebody to write a rule to kind of predict what kind of combinations of conversations that somebody can use to book a table, right? So this is another case where this text of yours, which now got converted from your sound bytes, sound input on the phone, will go through another machine learning modeling process, which is for understanding text, and not only understanding text, a complex variant of it, which is understanding conversations. So essentially, this is going to be a chatbot, or rather something like a chatbot, or which is also called conversational assistant. So this one is going to take your text input, right, and have been trained on loads or millions and millions of those conversations, and trained with paired responses. right? So it knows that if this is a conversation, this is a possible response. If this is a conversation, this is a possible response. So it has been trained on millions and millions of such conversation combinations. So that is another model that is working. So every time you are calling up, somebody calls up, these two models are there in play at the background of a conversational assistant, and these are all happening through machine learning. So there are multiple entities that are in play. The data that the data that is being used, so which is in this case first the voice, and second the converted text, and it leads to natural language processing. And the second thing is the algorithm that is reading or studying that data, the data input, and converting those data inputs into models, which can now convert, number one, in the number one case, convert your sound bites into text, corresponding text. And in the second case, in the conversational assistant, take a conversation or take a question, right, or a sentence in your conversation, and give you back an appropriate response, right? So these three things are in play. One is the input data, second is the algorithm that works on the input data, or learns from the input data, and it creates a model, okay, which finally gives you answers to questions or responses to conversations, right? So this is one case of voice assistant. So let's say, for instance, you have we take another example of product recommendations. So product recommendations are or let's say stock price prediction. So here you have huge amount of data, time series data, that day and time, and for over let's say 3 years, and stock prices during every day and every hour, etc., etc. So you have a huge amount of data on stock price movements for specific stocks, and you feed it into a machine learning algorithm. The machine learning algorithm learns the patterns, learns the trends over the last 3 years data that you have fed it, right? So at the end, it kind of creates a system of rules, or which is called a model, which is later on going to be used by you. If you say that, okay, I want to have a prediction of this stock price 1 month from now, and it is going to give you back a prediction based on what it has learned from the last 3 years data. Okay, now whether or not that is going to be correct, there can be other factors, new factors that may come into play in the market, etc., etc. So the reliability may be a little suspect, but more or less with a fair degree of accuracy, may not be 100%, but with a fair degree of accuracy, these models can predict stock prices quite well. So these are some of the examples of machine learning usages, right? Now let's understand what is the difference between the traditional programming and machine learning modeling, right? So in traditional programs, what happens is that let's say you are writing a Java program, or you are writing a Python program, which is not machine learning, which is your traditional programming. Now what happens is that somebody who has a requirement, your business, or let's say your stakeholder comes up with a requirement that I want this functionality, this screens, this fields, etc., etc. So clearly defined requirement and rules that have to be there in the application that they require you to develop. Now this is a deterministic situation. In a deterministic situation, what happens is that the rules that have to be implemented or incorporated or encoded in the programs are known from beforehand. Okay, there is no role of data except for testing in writing the programs, right? So you know the set of rules, you encode the rules in the program, then you use the data to test the rules whether they are correct or not. That is traditional programming. In the machine learning or data science predictive analytics modeling, what happens is that it's completely different. You are not writing any programming rules, right? You are going to use your algorithm, which is going to write the rules for you automatically. Now, how is it going to write the rules? It is going to look at the data, it is going to find out the patterns, and it is going to encode those patterns in the way you require it to encode it and give you the model. Okay, so in the stock price prediction case, what happens is that you have given it last 3 years worth of stock price data, every day opening price, closing price of a particular stock. Okay, so let's say Reliance Industries stock price. So every day you have a opening price and a closing price, and for the last 3 years you have this data. So this data has a trend, it has seasonality, it is connected to various market conditions or market incidents, and then your model learns all of that and it gives you predictions, right? So let's say you wanted to know 1 month later what is going to be the price, it gives you predictions, right? How did you write any rule in that? You did not. Who wrote the rules? The rules were found out by the algorithm and encoded in the model by the machine learning algorithm in this case, right? So that is the difference, basic difference between traditional programming and machine learning programming. There are various types of machine learning algorithms. For instance, you have supervised learning, unsupervised learning, semi-supervised learning, reinforcement learning. So quickly, what are supervised learning? Supervised learning is where you have a target value against your input features available. Now, what does that mean? That means, okay, let's take an example. Fine. So let's say you are working for a financial institution. Let's say you are working for a bank. Okay. And this bank issues credit cards to its customers, and there are a lot of transactions that happen every day using their credit cards. And now there are some of it which are fraudulent, right? It happens, right? I mean, fraudulent transactions happen. There are fraudsters who try various tricks, and they defraud customers, they defraud banks for looting money. Now, there is a small percentage of credit card transactions which are fraudulent. Now, what happens is this bank wants to get a machine learning model done which is going to learn from the past transactions and be able to predict that which of the future transactions are potentially fraudulent. So previously it used to happen manually, somebody scanning through experience, etc., etc. Some tricks used, manual tricks, some automations were there, but nothing was very reliable, and nothing was really automated, sort of say. Okay, so if that is the case, that we want to make a machine learning model, how will we do it? The training process that the algorithm has to go through has to have two elements. One is the input feature, so the transactions, okay, the credit card transactions, individual transactions. So historically, let's say the bank gives you say last 3 years worth of credit card transactions. Now the other thing that you need apart from those transactions is that which of those transactions are fraud and which of those transactions are non-fraud or valid transactions, right? So that's called a target value. The features of the transaction are called the input feature or predictor feature, right? So in cases where you have the target feature available, okay, the target feature or the target level available, that is called supervised learning. So you are learning, your algorithm is learning the relationship between a set of predictor feature and a target feature. In unsupervised learning, it's different. The target feature is not available. So let's say, for instance, you are working for a e-commerce company, and in that e-commerce company, the e-commerce company wants you to create a model which is going to tell them the various segments or groups of customers who have similar behavior. They want this customer segmentation done because they want specific types of promos to be built for targeting different groups of customers, because different customers have different purchase habits, and some people, some folks have the similar spending habit. Some folks shop at the same time of the day. Some folks shop for similar items. So let's say for somebody has liking for buying a lot of decorative home decor items, right? So if we get those kind of similarity or clustering or grouping between customers, and we can segregate them. Okay, if somebody has some group of customer from my whole list of customers have a liking for say white goods or say decorative items, I want to target specific merchandise to them. So somebody, the group of customers who are liking for white goods, so we will target them with TVs and fridges and stereos and Bluetooth speakers and mobile phones, etc., etc. Okay, so this customer segmentation, while doing this customer segmentation, you don't have a target feature, okay, because it is unknown to you as to what you are trying to find, right? In a credit card transaction case, you know exactly what you are trying to find out, but in this case you don't know what you are trying to find out, what clusters exist. So this is unsupervised learning. Okay, in semi supervised learning, it's a hybrid between supervised learning and non unsupervised learning. So say for instance in case of Google Photos, right? So you upload your photos in Google Photos, and Google Photos, so for images where there are people there, Google Photos is ask you that can you tag the name of the person in the picture, right? So it is going to ask you once, and after that it is going to automatically, so for any subsequent picture, it is going to automatically tag them with the that particular person's name, right? But sometimes it will also ask you to re-verify some of the labels, some of the person's labels, when it becomes a little less confident as to which person is this, right? This is a case of semi-supervised learning. So basically it starts from a supervised learning, so you tag images with the person's name, and then later on it keeps on building its database that you add subsequent 10 images of the same person, and it keeps on tagging it, and then that creates its that reinforces or extends the learning process for the machine learning model that is behind it in terms of image recognition ability. And sometimes it comes back to the supervised process again by asking you to re-verify the labels, right? So this is one case of semi-supervised learning. And the reinforcement learning is quite interesting, which is used for cases like games, right? So let's say for instance you heard that the computer beat the world champion for Go, the game Go, right? It's a board game now, which was thought to be an impossible task for a machine. Then you have heard about the use case of driverless cars. Now what happens is that in these kind of cases, the machine has to learn by experiencing success or failure. So it is going to be an agent in working, and the agent will perform a task, and the agent will be given a reward or a penalty. Okay, so if the self-driving car takes a correct turn, it receives a penalty, the model receives a reward, and if it takes a wrong turn, the model receives a penalty or a negative reward. Okay, and the model or the agent's task is going to be to reach its destination or reach its goal with the maximum amount of rewards or the least amount of penalty. Okay, so very interesting field of study, and very complicated or very sophisticated use cases that have been developed in this area, which is on reinforcement learning. Now we have mentioned that in machine learning that the role of data is very important, because your algorithm, you are not writing rules like traditional programming, but your algorithm is learning rules from your data. So hence the importance of the data in your machine learning or data science predictive modeling is going to be extremely important. So hence it is important that we understand the types of data, the different types of data that our models are going to be, or algorithms are going to be working with to determine models or produce models. So we work with numerical data, continuous numerical data, categorical data. Continuous numerical data is like 1, 1.1, 2.3, 4.5, etc., etc. So these are continuous numerical data. Categorical data can be good, bad, very good, excellent, etc. Okay, time series data can be, if you can relate to the stock price data. I mean, you have dates and times, and corresponding to the dates and times you have stock prices, right? So these are called time series data, right? So those are types of data. Then you have text data. So let's say I'm giving this delivering this webinar to you. So what I'm delivering is actually text data. I mean, this is sound data. It can be converted into text data, or whatever is written on this slide is text data, right? This can be processed and this can be summarized, and a lot of things can be done with it. So natural language processing tasks are going to use text data. So let's say, for instance, conversational assistant, that example that we have taken, it processes natural language text. So essentially it learns from millions and millions of conversations and learns to converse like a human being. Okay, then you deal with image data. So let's say, for instance, tasks like image labeling, which is a very tedious task if it is done manually, but then with image recognition algorithms like convolutional neural network, etc., image recognition tasks have become very easy nowadays, and with very sophisticated model, we can achieve a very high degree of accuracy in image recognitions, right? So there you deal with image data. So these are some of the types of data that you generally use in machine learning. Now we come to today's topic, which is classification problems. Now there are different we touch upon a couple of different types of problems. So let's say, for instance, there's a couple of very common cases that I used while teaching machine learning problems. So one such example is prediction of house prices. So let's say one real estate agent has tons of data of property sales, and those transactions contain features of the or attributes of the properties that were sold by that agency, and for each of them it contains the price of the property. Now they wanted to create a model wherein they will feed the features of a new property that has come for resale, and the model will be able to generate an approximate estimated sale price from the features that are fed to it. Okay, so this is a problem that is going to be a regression problem. Okay, the output of the regression problem, the model in a regression problem is a function or the relationship between the predictor variables. So in this case, the house price, or sorry, the house property features, and the target feature, which is the house price. And in this case of regression problems, the target feature is of continuous numeric type. Okay, and what is continuous numeric type? We said 2.1, 5.6, 1 to 5, 6.89, something like that. I mean, these are continuous values, right? So between two continuous values, you can have an infinite number of values, right? If you say between 2.1 and 2.2, how many number of values you can have, right? If you extend the degree of or the number of decimal places, you can actually have infinite number of values between 2.1 and 2.2, right? Yeah, going to the second decimal point, a third decimal point, fourth decimal point, you can have infinite numbers. So these are continuous numeric variables, right? So that is in case of regression problem. The classification problem is slightly different. Here also, the regression problem, as you got from the example, is an example of a supervised learning process, right? So going back in the classification of the different machine learning techniques, we said that in supervised learning you have predictor feature and a target feature, right? So from the example that I have given of regression problems, you would have understood that that is an example of supervised learning. Classification problems are also cases of supervised learning. Okay, here also you will have a set of predictor features and a target feature. However, the big difference between regression problems and classification problem is that regression problems have a continuous numeric variable as its target feature. The classification problems have a discrete value as its target feature. Predictor can be anything, right? Predictor can be Boolean values, predictor can be numeric continuous values, predictor can be numeric discrete numeric categorical values, textual values, etc., etc. That is same for regression problems, that is same for classification problems. Different algorithms have different appetite for different types of predictor features, but nevertheless your predictor features can be anything, right? So you understood the difference between classification problems and regression problems. Now, if you recall that I was taking this example of the credit card fraud detection modeling, okay, and we said that your goal is to find out which of your transactions are fraudulent or not, right? And this is, so what is going to be the output from the model? You are looking for a yes or no, 1 or 0, right? If you say 1, that means it's a fraudulent transaction. If the model outputs 0, that indicates it's a valid non-fraudulent transaction, right? That is the outcome that you want from the credit card fraud detection model, and it's a very classical case of a classification problem, okay? And it's a case of a binary classification problem where there are two possible outputs from the model. Now, how does the modeling happen? You have a classification algorithm, you have input data which have predictor features and the target features. So in case of the classification, the credit card fraud detection problem, you have, let's say, last 5 years worth of transaction data, credit card transaction data. So your classification algorithm learns from those last 5 years of transactions, and what we said that those fields in the credit card transactions are the predictor features, and you also expect a label against those transactions for each of those transactions. If there are 1 million transactions that they have given you from last 5 years credit card history, each of those 1 million transactions should be labeled as 1 or 0, indicating they were fraudulent or non-fraudulent. Okay, so you have taught the model using the classification algorithm as to what a fraudulent transaction looks like or what a non-fraudulent transaction looks like. Okay, so this is going to be the goal for your classification algorithms, right? So basically, just like regression problems, here also the predictive modeling for classification algorithms is the task of approximating a mapping function. So basically creating an approximate relationship between the input variables, or what we call predictor variables or independent variables, that is the X feature sets, to discrete output variables, that is the Y feature, which is in the example that we were taking 0 or 1, that indicates a fraudulent or non-fraudulent transaction. right? And these output variables are sometimes called labels or categories. That is fine. And we spoke about, in our case, it's a binary classification problem, but there could be examples where you have a multi-class classification problem. So let's say, for instance, you have a image detection model, and there could be possible 20 different types of images that you may have to decide from. So you have been using a deep learning model, or and you have created a model for image detection from input data which comprised of a lot of animal images in different poses, different scenarios, etc., etc. And you have fed it labels that this is a tiger, this is a cat, this is a dog, this is a owl, or this is a eagle, or something like that. Okay, so each of those have, so in this case we were saying that there could be 20 possible types of animals, and then once a model is created by learning, so your model will be expected to output, given an image, what animal is that. Okay, so that's a multi-class. So the output can be any value, any one value from a possible list of 20 values, right? So that's a multi-class classification problem. But also there is another interesting type of classification problem, which is multi-level classification problem. So it could be one image, but that one particular image may require multiple labels. Okay, so if one image requires multiple labels, that becomes a multi-level classification problem. Now, classification problem outcomes can be of two types. One is the class itself. So in case of the credit card classification problem, fraud detection problem, what we said we want is we want a prediction which is going to be 1 or 0. 1 indicating it's a fraudulent transaction, 0 indicating it's a non-fraudulent transaction, right? That is one type of output that we can expect from the classification model. Now the other kind of output that typically classification algorithms output is the probability. Okay, so for instance, your model may say that, okay, I am not able to say it is 1 or 0, but I am going to say what is the probability that a particular transaction is fraudulent or non-fraudulent. And I can say that for a particular transaction, I am 75% sure it is a fraudulent transaction. Okay, based on patterns it has learned during the training process, it says that, okay, I can say with 75% probability that it is a fraudulent transaction. Now it is up to you to decide a threshold value. Okay, so you can tell, okay, I take a threshold value of 50%, and okay, taking that 50%, you tell me whether it's whether the final output has to be a 1 or 0. So then the prediction says that, okay, it's a fraudulent transaction. Okay, so these are the two types of outputs that can come out from a classification algorithm. All right, now there's a couple of problem statements similar to the one that we have been talking about. So let's say an insurance company says that our customer churn has increased almost 10% from last year. We would like to predict which customers are likely to leave us. So basically this is a customer churn prediction. So let's say you are a subscriber of Airtel, and Airtel in recent days are losing customers. People are going to leaving Airtel to go to Vodafone Idea. Now it is important for Airtel to control that. It is important for Airtel to be able to retain their customers. So what they want is that, okay, so they have a lot of data about customers and their transactions, their history, etc., etc., and they want a model to be created by which they will be able to predict which of their current set of customers have a high probability of leaving Airtel. Okay, very valid problem statement, and these are very common problem statements nowadays companies work with. Which of my customers, I mean any company for that matter, I mean customers come and go, say if somebody is not satisfied, they leave for another. I mean I purchase from Amazon, but tomorrow I may start purchasing from Flipkart. So all of a sudden Amazon will say that okay, this guy is not coming to us anymore, right? So Amazon wants to predict that okay, what are the typical behaviors, or rather which of my current customers are in the threat of leaving us for another service provider, right? So very typical case. So what do we want? I want a prediction in this case. Given the history of this customer, tell me, one, if this customer has a high probability of leaving me, or zero, if this customer is likely to stay with me. Typical classification algorithm. So there can be similarly different different problem statements, very common problem statements of classification algorithms. Now let's come to what are the different classification algorithms. There are lots of different classification algorithms that are available in the in machine learning and data science predictive analytics. Now we take some common algorithms, and we give a brief overview of that, and we will at the end we will take a little small example of how classification algorithms work in code, and do a comparison of a simple case as to what is the result coming out of each of these algorithms in using Python. Right, so we have classification algorithms like logistic regression, naive-bayes, stochastic gradient descent, k nearest neighbors, decision tree, random forest, support vector machine. So these are the ones that we are going to talk about. But apart from that, there is a new generation of algorithms that have right now come in, which are deep learning algorithms. And deep learning algorithms also perform regression tasks as well as classification tasks, and they perform better than some of this conventional or traditional or kind of currently popularly used classification algorithms. So the usage of deep learning is also kind of proliferating. So we are not going to look into deep learning. That's a different ball game altogether. Next week we have an introduction to deep learning session, and you are welcome to join us for that. So we will take a case, and we will see how deep learning is what deep learning is, and how we can perform some classification or regression tasks using deep learning. And we are going to do it using TensorFlow and Keras. Right, so for today we are going to take a brief introduction to each of these 7 or 8 classification techniques. Now one thing is for certain, that each of these, again going back to our definition of or difference between machine learning and traditional programming, we don't write rules in machine learning. These are the algorithms which study the patterns in the input data, and they encode the rules or patterns in the input data in the form of models. And in classification algorithms, what we have said in the definition is that the classification algorithms in the classification model, they encode the relationship between the predictor features and the target feature, which is the class or the label. Right, so our model created by these classification algorithms are the relationship between the predictor feature and the class label or the target variable or the target feature. Okay, different names are used. So if that is the case, what does logistic regression or naive-bayes or stochastic gradient descent use at the background? So we're going to get briefly into that, but we can't explain everything. Each of these algorithms have a mathematical formula at the back of it, right? We can't get into the nitty-gritties of the mathematical formula in this session. We will probably have separate session on each of these, and you can join one of our courses to learn in detail as to how a logistic regression is carried out. But each of them have a mathematical formula working behind them, which looks into the data and which creates those relationships between predictor and target features, right? And for each of them, the mathematical formula and the working formula are different. Okay, so these are mathematical formula, statistical techniques that are used in creating those rules. So we take an example, a worked out example. This is our input, sample input data in solving a classification problem. So we have a disease detection problem here. So, what is the case? The case is we have a clinic has patients data, and for each of the patients, so we have the age and sex and resting BP value and cholesterol value and fasting blood sugar value, resting ECG value, and etc. etc. So all these are x1, x2, x set of features which are our predictor feature in the input data set. Now we also have the target data set here, or sorry, the target feature here. So we have a 1 or 0 in the target feature, right? So when training, forget about this last feature, it is not there. Let's assume that this is not there. All right, we'll come to it a bit later. So for our classification problem, for any of the classification algorithm, we are going to feed these x1 to x8 features as predictor variables and this feature as the target variable, right? This has to be understood. Now what the classification algorithm does is it's going to create a model in which it is going to create a relationship between this x1 to x8 features or variables and y variable, in the sense that after the model is created, if you feed one of these or a different set of values against x1 and x2, sorry, x1 and x8, then it will be able to predict whether it is a 1 or 0, because it has studied the pattern, and you are not giving it 5 observations. So these are 5 records that we have, 5 records or observations in your input data set. You have to, for proper learning, appropriate learning, you have to feed it with lots of data, let's say in thousands and blacks, right? So only then it is going to be able to kind of be sure of the patterns that are there in the data set between the predictor features and the target feature, right? And then only if you input a new set of values against x1 and x8, it is going to give you a value back whether this person has a disease, let's say a heart disease or not. So 1 meaning that with these values this person has a heart disease, and with these values this person doesn't have a heart disease. So after learning these patterns, your model should be able to predict them accurately or reasonably accurately, right? So that is our classification problem, and this is a kind of sample data. Now coming to logistic regression, what happens is that it uses something called a logistic function or a logit function, which looks like this, right? Now it's a type of regression equation. So if you have known the linear regression, it is modeled as y equals to, say, theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus theta n xn plus say c or theta 0, something like that. Now here in this case, this is a logit function. What happens is that in this expression it has this model parameters beta 0, beta 1, x1, beta 2, x2. So if I generalize this expression, this is the regression equation in the logit expression, which is beta 0 plus beta 1 x1, beta 2 x2, beta 3 x3, etc, etc. Okay, so what this logit function does is that with all the values of the combination of x1, x2, x3, x4, it learns this beta 1, beta 0, beta 1, beta 2 parameters and able to output a probability. The logistic regression or the logit function output is a probability value. Now when it learns the relationship of this when it learns the parameters, the logit function parameters beta 0, beta 1, etc., etc., it is able to predict the probability value of the rephrase it. It is going to be able to give you the probability value of your output being 1. So you have to be very clear here. The probability that is output from this logit equation is the probability of the class being 1. So if the output from the logit model is 20%, then what is the class value? The class value is going to be 0, because the probability of 1 is 20%. So that means the probability of 0 is 80%. So that is exactly 1 minus that percentage. So this is the logistic regression, and logistic regressions use our linear regression model. Logistic regression also use a gradient descent approach. So we'll not talk about gradient descent approach. We'll touch upon gradient descent approach when we go to another algorithm called stochastic gradient descent. Okay, and it uses you would know that for any machine learning model, they work on the basis of the optimization of the model. So optimization of the model means that learning the optimum parameters, model parameters. In this case the optimal the model parameters are beta 0, beta 1, beta 2, etc. Now in logistic regression case, it uses something called a maximum likelihood function as the loss function. So the maximum likelihood function is actually the probability values that it learns from, or it outputs from a particular combination of beta 0, beta 1, beta 2, beta 3, etc. for your output class level being 1. So if it for all the data points, if it multiplies all the probability of the output being 1, that gives the maximum likelihood value, and maximizing the maximum likelihood value is going to be the motive of the gradient descent approach for logistic regression. It's a mouthful. I know that most of it is not making sense, but to touch upon each of the classification algorithms, this is probably at the level we can leave it to at this moment. But feel free to join one of the subsequent workshops we will definitely organize on some of these classification techniques in detail. So, and there we can explain with a worked out example as to how the calculation actually works for logistic regression and how the maximum likelihood function is calculated, etc. Okay, so that's logistic regression. And one point about logistic regression, I mentioned that it outputs a probability. Now you say that probability can be 20%. In this case you interpret the class level as 0, and if it is 80%, you interpret the class level as 1. But on what basis? What is the threshold that you have taken? The threshold of probability beyond which you will treat the class level as 1, and below which you will treat the class level as 0. So there is a threshold value that you can attach for the logistic regression, and there is also a technique that can be used to find the optimum threshold value, which is going to give you the most optimal parameters of the logistic model. Okay, or rather not the most optimal logistic model. I mean, basically it is going to give you the maximum accuracy or other metric of the classification model, that we will see what metric of classification models that normally used. So it is going to give you, let's say, the maximum accuracy from the model, right? And naive Bayes is a classifier that used to be in have a lot of popular uses. Let's say, for instance, you have this thing about your mailbox, that when you receive mails in the morning, your some of your mails get directed to your spam mailbox, right? How does it happen? There is a machine learning model that works in at the background, and right now there are more sophisticated models, but earlier days there were naive Bayes models, and naive Bayes using some text classification, or rather some naive or kind of very elementary techniques on text representation, like using models like continuous bag of words or bag of words models. It could classify or create patterns by which used to determine whether a mail is based on the texts used in the mails. It used to classify whether a particular mail is spam or a ham. Ham is valid mail, not a spam mail, right? So naive Bayes works on the basis of probability techniques. So this is one of the areas of probability. It's part of statistics, and probability is statistics, and it works on the basis of a statistical formula, which is this one, right? But before looking into the formula, we'll look into what is there's a assumption called the naive assumption. The naive assumption is mandatory for naive Bayes to be able to act on a particular set of data to create a properly working model. Now, the naive classifier assumes that the value of a particular feature is independent of the value of any other feature given the class variable. Now, what that means in simple terms is that if you have 10 features in your 10 predictor features, you have to make sure for a naive Bayes model to be successful on that particular set of input data, that none of these features have a relationship between any other. Okay, not a x7 derived from x8, or doesn't have, I mean, any inadvertent relationship between x3 and x5, etc., etc. So the assumption is that all features are independent. There is no relationship existing between the variables, and they are completely independent of each other, right? I mean, none of the features are influencing any other feature. Now, the formula says that the formula has two distinct parts. One is prior probability, likelihood, and the posterior probability. The prior probability is here. The probability is an outcome from the model. The probability of the class meaning 0 or 1 in our classification examples that we were taking previously. The possible classes are 0 or 1. So we are trying to derive the probability of a class being, say, 1 given a particular set of values against your predictor feature, which is denoted by x. This expression is called the posterior probability, and the posterior probability is something that we are trying to find out. And if you remember, the probability is also the output for your logistic regression equation, the logit equation, right? But in that case, it was using a completely different mechanism. It was using a gradient descent mechanism. It was using the maximum likelihood function, and it was using the logistic regression, logit function. Okay. Now, there are these elements from your input data. So if you recall the input data, these are the elements that the model derives from the combination of values from your input features. Okay, so basically it finds out the probability of the combination of values that it has in its predictor features given a particular class. The probability of the class itself in the entire set of data, and the probability of that combination of input feature values in the data set. Okay, again, detailed explanation can be in a session that is dedicated to naive Bayes or in our course, but this is more or less what the model tries to find out from the data, from the input data set, and calculation of these values are completely very easy and very fast. And now once this probability figures are kind of extracted by the model, the predictions are normally very fast because it uses the probability values. Okay, so some of the points about naive Bayes is that extremely fast predictions, easily interpretable because it works on the probability values. The calculations can be also made using Excel sheets if you want to do so, if you want to validate your results, etc. The naive assumption should be made, and it also works with high dimensional data. It doesn't have any complaint with multi-dimensional, major number of features, input features. So let's say you have a data set with 100 features, naive Bayes works perfectly fine with that. Okay, now stochastic gradient descent requires an explanation of the gradient descent algorithm itself. Now, gradient descent algorithm is a generic algorithm, and gradient descent algorithm is used very widely across many algorithms, including huge plethora of deep learning algorithms. So understanding gradient descent is extremely important for any machine learning data science professionals. Now, what is gradient descent? Gradient descent is not very difficult to understand. So essentially, gradient descent finds out the gradient between two values in an equation. Now, when does that happen? That happens, let's say, for instance, in case of you are trying to find an equation in case of linear regression, let's say, for instance, and we know that in linear regression the cost function used is mean squared error. Okay, or for that matter, if we go back, we said that for logistic regression we use the loss function, which is the maximum likelihood function, right? Now it has an equation, okay, which is a cost function. The cost function has an equation. So let's say for logistic regression, the maximum likelihood function, we said the multiplication of, or the product of, all the probabilities of the class being 1 for each of the data points is the maximum likelihood function. Or in case of linear regression, the cost function is the mean squared error. So in that case, what gradient descent does is that it starts by using a random set of values for the model parameters. Okay, and what is the set of model parameters in case of logistic regression? The model parameters are beta 0, beta 1, and if you have more variables, more predictor variables, beta 1, beta 2, beta 3, beta 4, etc. These are the model parameters. And what is the goal of your cost function? The cost functions, rather the algorithm's goal is to create a model with the optimum values of beta 0, beta 1, beta 2. Okay, so cost function is used to find out the optimum combination of the model parameters. How? In case of MSE has a formula. The mean squared error has a formula. The gradient descent algorithm uses that formula, and for every combination of the model parameters, it finds out the value of MSE. In case of logistic regression, for every combination of the model parameters, it finds out the value of the maximum likelihood function. In case of MSE, in case of linear regression, gradient descent tries to tweak the model parameters, that is the combination of beta 0, beta 1, beta 2, beta 3, etc., it tries to minimize the value of MSE and try to get a combination of beta 0 beta 1s which yields the minimum value of MSE. And in case of logistic regression, it tries to get the set of model parameters, that is beta 1, beta 0, etc., which yields the maximum value for the maximum likelihood function. Okay, so that is the cost function, and that is the approach that gradient descent takes, right? So now what happens is that while performing this approach, it has to go through, I mean, starting from a random set of values against beta 0 beta 1, it has to go through a lot of steps. Okay, and each step it tweaks the parameter a little bit and finds out the gradient and see that, okay, am I moving towards towards the direction that I am supposed to move. In case of MSE, it has to go down, and in case of maximum likelihood function, it has to go up. So it finds a gradient and it has to see that am I going down or going up, and is it the direction that I want to go. And if it goes the wrong way, then it tweaks the parameter again and keeps on going like that till it finds some minimum value for MSE and maximum value for maximum likelihood function. Now, while doing that, at every step it recalculates the gradient, recalculates the next step and the gradient. It uses the entire set of input parameters to do that, to find out the value of the cost function. Now that is very inefficient. It needs a lot of computing power, and the process is very slow also. Now stochastic gradient descent does the same thing, okay, but it lets the gradient descent process pick up only one observation, a randomly picked observation at a time, for tweaking its parameters and finding out the next gradient and moving towards the minimum value of the cost function, minimum for MSE and maximum for maximum likelihood function. So that is stochastic gradient descent. Stochastic actually means random. Okay, so stochastic gradient descent is gradient descent. Just the only difference between gradient descent is that it picks up a random observation instead of the whole input data set. Okay, so SGD classifier is our next classification algorithm. K nearest neighbor is very easy, funny mathematical formula. So what happens is that you have classes in the data set, and you can see the classes, this orange data set, data that belong to one class, and this blue data that belong to another class, right? Now in K nearest neighbors, what the formula that it uses is that given a new data point, we have to determine which class it belongs to. Does it belong to the blue class, or does it belong to the orange class? Now how does it find that out? It finds that out based on this saying, birds of a feather flock together. So whichever group I am nearest to, I belong to that group, right? So that's a simple proximity based calculation. So what happens is that you are to determine a value which is called K value, and that is where the name came from, the K nearest neighbors. Let's say you say K is 20. So for this new data point, what it does is that it finds out its distances, and in case of distance in a two-dimensional surface or any dimensional surface, it's Euclidean distance. So you need to look up what is Euclidean distance. I mean, there's one of the most easiest or the easiest distance measure, or the most commonly used distance measure. So essentially that gives the distance between this. So we find out the distance between this new value, a new data point, to all the other data points. Okay, and our K value we determined is 20. So it takes the 20 nearest data points, and then it finds out how many of them, those 20 nearest data points to this new data point, are belonging to the blue class, and how many of them are belonging to the orange class. Now whichever has a larger number of values. So that means that if there are more number of blue points which are closer to this new point than the orange points, then the class of the new point is going to be determined as the class of the blue point. Okay, funny simple theory that birds of a feather flock together. Now, what is the downside of this? The funny one other funny side is that there is no model you are building here, right? The model is essentially the whole data set, and that is the downside. So if you have a huge data set, it actually memorizes the entire data set, because for every new data point you have to calculate the Euclidean distances from the entire data set, right, for with all observations. So that means that your model actually has to contain the entire data set. The model is actually the data set because it's a distance based algorithm, right? So that is a little downside of that. And it gets significantly slower with the number of examples go bigger, as you can easily understand. Now, decision trees are very powerful algorithms, and they use some sophisticated methods. So what happens is that in decision trees, you create a tree-like structure or tree-like hierarchy of rules. Okay, so say for instance you have a rule like if1 is a feature, f2 is a feature, f3 is a feature, f4 is a feature on this data set. So you have a decision node here, or a root node here, which says if feature 1 take all the input values, if feature 1 of all those input values is less than equals to 0.45, then whichever observations fulfill this criteria, send them to this decision node. Whichever do not fulfill that criteria, send them to this node. Okay, and so on, right? It creates this branching structure of, or branch structure of decision nodes, and each of the decision nodes have a feature in there and a threshold value. Now the funny point is, how do I decide if I have a data set which has say 10 features? How do I decide which is going to be my root node? Because I need to create the right set of combinations of feature and conditions, right? Feature and threshold values. So the right combination has to be there, right condition has to be there. Now this is based on a formula or a measure that is called Gini index, and another one called entropy. So for each layer or each step of the tree building exercise, the decision tree algorithm calculates the Gini index or the entropy value, which are essentially measures of purity. So we can't go into, we are running out of time, we can't go into the nitty-gritties of what is Gini index and entropy, but that is what it tries to find out. The lower the Gini index, it tries to find out the feature and threshold combination from the data set where the Gini index for that particular layer or the entropy value for that particular layer is the lowest. Okay, that is going to lead to an uniform or pure distribution of class labels for decision trees. Okay, more on that in a subsequent session on decision trees, but that is what it does. But their versatility of decision trees is that they are very powerful. They have a problem of overfitting. They can go into nth layer of structuring tree-like structure of decisions, and that becomes very complicated and leads to overfitting. Predictions are very fast. Decision trees can work with different types of data. It can even work with textual data. Data need not be converted into categories. Textual categorical data need not be converted into numeric values. So its versatility also lies in the kind of data it can work with, etc. And the overfitting problems can be fixed by using pruning hyperparameter or regularization hyperparameter. So we will see in our decision tree session. Random forests are built on top of decision trees. Now forest, what is there in forest? Forest has trees. Now random forest actually has decision trees. So it's an ensemble technique which is comprised of hundreds of decision trees, and you can mention how many decision trees you want in a random forest. The optimization algorithm of random forest works in the same way as decision trees. Random forest also uses the entropy and Gini index values for optimization to create the individual structure of the decision trees. But what happens is that it uses something called a bagging process. So this is your entire data set. Random forest is going to create small subsets of this data set, this overall data set, and it's going to apply individual decision trees on this individual bags of data from the input data set, right? And then each of these decision trees will be on a randomly picked up subset of data and a randomly picked up subset of features. So this whole process is called a bagging process, and this is what random forest does. Again, it uses a voting mechanism. So voting mechanism means that let's say the output from this is 1, this is 1, this is 0, this is 1, this is 0. Now 3 of them have given the class level of 1 as output, 2 of them gave up class level of 0 as output, right? Because each of them individually is a decision tree model. It uses a voting mechanism, so the final class level is going to be 1 from this random forest model, because it uses a voting. So 3 of them give a classification level of 1 and 0 have been given by 2. Support vector machine, I think this is the last one. Yeah, support vector machine is a classifier which is again very powerful. It uses something called a street. Okay, so let's say you have this 2 classes in your data, and this green classes and this green dots. So this is your x-axis and this is your y-axis. Of course, you do not have one predictor variable in your modeling process. You have, but for visualization we are using a 2-dimensional data. So you have these green values and you have your red values. So 2 distinct classes of data are available. Now what support vector machine does is that it creates a path. Now what is the path? The path has a separation line, the optimum separating hyperplane. So this is the optimal separating hyperplane, and then it has 2 boundaries on each side of the optimum separating hyperplane. Now this, what is the intent? The intent is to create the widest possible street between the 2 classes, right? So whichever direction it can create the widest possible street using an algorithm, it will create that widest possible street, right? Now you see there is a problem here. The problem here is that if there are outliers of greens here or outliers of red which are positioned here, then you have a problem. Then you can't have a clear wide street between these 2 classes, right? So there you have to kind of make a kind of compromise as to what is your motive. The motive of support vector machine is to create a wide street. Now why does it want to create a wide street? Because the wider the street is, the generalizability of the model is going to be higher. The generalizability meaning that for any unseen class it will be able to classify better. So but then you have this outlier problem, and support vector machine expects the data to be linearly separable. Okay, so there has to be a clear linear separation line that should be possible between these 2 data, but in case of outlier you can't have that. Hence support vector machine uses a hyperparameter called C parameter. That C parameter lets you use a trade-off between creating a wide street with outliers or creating a street as wide as possible without any outliers. Okay, so if you are strict against having any outliers, then your street is probably going to be smaller or narrower, not a wide street. But if you make it wide by allowing outliers, it is going to be more generalizable, which is going to be better for your predictions with unseen data. Okay, so that is support vector machine, and it can work in high dimensional spaces with relatively low number of data points. It can be successful. As I explained, it does not perform very well with data sets where there is more noise and target classes are overlapping. So if you have outlier classes, then it doesn't work that well. So it actually expects clearly linearly separable classes. Quickly, we will get into how we measure the accuracy of classification matrix. The classification, the basis of classification models performance evaluation is something which is called a confusion matrix, and the confusion matrix look like this. Now, what can be the output from classification matrix? Classification models. We look back to our input data set. This. So you have this predictor features. You have your target value, which is, these are the target value we know that there are, and there is a ground truth, and this is the predicted values from your model. So once your model is created, you pass on the same data, and these are the predicted values. So you have predictor features, you have y, which is ground truth, you know those are the actual y values, that is a class level, and the predicted class level from the model. So this is what you have. Now what you need to do is to find out the performance of your class is that you need to compare between the class levels which are actual and predicted. So this one is clear, rightly done. This one is not correctly done. So your actual level is 1 and the model has predicted it as 0. The other ones are same. So out of this 5, your model has predicted 1 as incorrectly, 1 incorrectly. In case of positive, it has predicted it as negative. Okay, so in the confusion matrix, the terminology is positive and negative, which is 1 and 0. With that understanding, let's understand how the classification matrix looks like. So from rather than going here in the template of the confusion matrix, let's look at a worked out example directly. So let's say we have 100 observations, okay, in our training data set. 100 observations meaning 100 records. Now positive are the 1 class level and negative are the 0 class level. This is the actual axis and this is the predicted axis. What does this cell indicate? 32 is the number of cases, number of observations in which the actual level was positive, that is 1, and the predicted was also positive, right? So this is good. 41 number of cases were actually negative, that is 0, and predicted also was negative, so this is also good. So this is called true positive in the confusion matrix definition, and this is called true negative or TN. Okay, so true positives are count of positive levels that the model predicted correctly, and true negatives are count of negative levels that the model predicted correctly, and these are the flips of that. So this one, 15 number of cases were actually 0 but predicted as 1, and 12 number of cases were actually 1 but predicted as 0. So these are false negatives and false positives, right? So that is count of positive, false positive is count of positive levels that the model predicted as negative wrongly, and false negative is count of negative levels that the model predicted as positive wrongly. So the accuracy is basically this plus this 32 plus 41, which is actually 73, divided by 100. So these four numbers come to 100 total. Okay, so accuracy is 73. Now there are a few other matrix that are used, which is I'm not getting into all of them, so but I'll mention a couple of them quickly. Say recall, and we will also look at precision. Okay, so precision and recall. So precision and recall formula is true positive. So recall is true positive divided by the true positive plus false negative, right? And precision is true positive divided by true positive plus false positives. Right, now we said accuracy for this particular case for our model, which is giving this confusion matrix, is accuracy 73. Why is it not enough for us to understand how well the model is performing? It is actually not enough. Now let's take this two examples. So we have a case where a clinic is diagnosing 100 people, 100 patients, and they found that there are 5 out of those 100 people who have heart condition, right? Now they are getting into a machine learning model, a classification model, and see how these models are performing. Okay, let's say our model is very bad and predicts every case as heart condition. So that means the model is terrible, that all of these 100 people, it says it is 1. So heart condition, having heart condition is 1, not having heart condition is 0. Since we are predicting everyone as having heart condition, our denominator, that is true negative plus false positive, is 100. Okay, so true negative and the false positive is actually 100 in this case, and the numerator, person having heart condition and the model predicting this case, is 5. So in this case the precision of such model is 5%, which is terrible, right? So essentially your precision is very, very bad. Why is it bad? Because all of your 95 cases where people did not have the heart condition are also predicted as heart condition. So all your 0 levels are predicted as 1. So you have 5 as true negatives in this case and 95 as false positive. Okay, so because you are having 95 false positives, your precision is coming down to 5%. So you see, now if we relied on the accuracy, we would have been wrong in these cases where you want to determine how many of your 0 level cases are being predicted correctly. You use precision. Okay, and recall is true positive divided by true positive plus false negative. Now in the same case, our denominator, true positive and false negative, is 5, and the numerator, which is true positive, person having heart condition and the model predicting the case's heart condition, is also 5, and hence the recall of this model is 100%, because 5 out of 5 level 1 cases have been predicted correctly. So although the recall of this model is 100%, it is still not a good model because your precision is terribly low. So in your case, you have to make sure, based on the problem statement you are dealing with, you have to make sure you are using the right matrix for evaluating your classification problem. So let's look at a small worked out example. So we are not going to perform any exploratory data analysis. We are actually going to do something pretty interesting. In a very small piece of code, we are going to run all the classification techniques, classification algorithms that we have learned about, I think all of them, and see the results on a small data set, small input data set. Okay, now what we are going to do is that we are going to perform the logistic regression, k nearest neighbors, decision tree classifier, Gaussian naive Bayes, support vector machine, and random forest algorithms. All right, so for to start with, we definitely import all of these libraries, all of these all of the classification algorithms from their respective modules from scikit-learn library. So that's done first, and then we take our mini data set for classification. So we have this little data set for diabetes diagnosis, and the class label, that is your predicted value, which is your target value, is 1 or 0, whether the person has diabetes or not, and these are diagnosis results. Okay, so these fields are diagnosis results, right? So pretty simple data set, and we are going to perform the classification algorithms on top of that. So basically we are going to use the training data. This is the training data. We are not going to do any train test splitting and exclusive testing. We are going to run this through something called the cross validation, k-fold cross validation technique, and we are going to run all of them, and we are going to capture the accuracy that they are coming up with after training using this data, and validation using the k-fold cross validation. And how it does that, I'll come to it in a moment. Okay, so with that, what we do is we create the x set, because you need the x set, and you need to segregate the x values and y values for your training process. So x is this expression, so that is coming from, so we convert our data frame into an NumPy array, and we take this value. So essentially we take the columns 0 to 8, 1 2 3 4 5 6 7 8 7th yeah, and those are the predictor values, and the 8th column here is the class label. Okay, now you have your x data, that is the predictor set, and the target label. Now what we are going to do is we are going to create a list, and this list is going to have the objects of this classification models. Okay, now after this is done, this is the list of model objects. Okay, so what are we going to do with this list of model objects? We are going to run it using a for loop in a cross validation, input it into a cross validation method. Now what this k-fold cross validation method is going to do is that it is going to take the models, okay, and the k-fold cross validation takes the parameter called n underscore splits. Now n underscore splits mean that create 10 segments in the input data set I have given you, right? So the k-fold is going to run the model, each of the model. So because we are feeding one model at a time to the k-fold cross validation method within this for loop. So first case, it takes up the logistic regression classifier, and it creates 10 segments of the input data set, right? And one of these segments, 9 of these segments, it is going to use for training, and one segment it is going to use for testing or validation, right? And it is going to come up with the cross validation scores for that particular run. Okay, so it runs in the for loop, it runs the logistic regression, linear discriminant analysis, k nearest neighbor, decision tree, random forest, Gaussian naive Bayes, and support vector machine, support vector classifier, right? It runs it within a loop, and it also captures the CV results, which is the result from the cross validation process, the k-fold cross-validation process, and the scores are stored into this structure called CV results, right? And the metric that we are going to capture in the CV results is accuracy, which we have stored in the scoring parameter, and we are passing that okay, for our cross validations please capture the accuracy metric for all your runs. Okay, so now the CV results have the accuracy scores coming out of all the classification runs. Okay, for logistic regression, linear discriminant analysis, k nearest neighbor, decision tree, random forest, etc., etc. And for each of them you see that logistic regression coming up with 77% accuracy, LDA is 77.3% accuracy, k nearest neighbor 72.6, decision tree 69, but random forest is 76.6. so what we said is that random forest is built on top of decision tree, and it makes it more powerful than decision trees. It's coming up with I think the best results of all of them. And naive Bayes is also performing very well for this simple data set. And support vector machine is also coming up with 76, which is close to random forest. So this is a nifty technique of running 7 classifiers in a very quick method, and capturing what classification score they are coming up with for this little input data set that we have used for diabetes detection. Now needless to say that this is not how you do it. I mean, this is just a demonstration. This is not how you do it in real life situation. And normally what you do is that you have to in your realistic cases, the data sets are going to be far more complex. You have to perform a lot of exploratory data analysis before your modeling process. You have to do feature engineering as part of the exploratory data analysis. And for all of these models, what has happened is that they have run with the default set of parameters, and each of these models, classification models, have various hyperparameters. Like say for instance, SVC has a critical hyperparameter called C, which determines the generalizability of support vector machine, which we have not used, or which we have not tuned. Random forest and decision trees have tendency of overfitting. I mean, they will definitely overfit if they are we do not use hyperparameters on them. So that's a thing that we have to do for random forest, etc., etc. So for each of them you have to use hyperparameters to tune your model well. And for each of them we also use cross validation methods to find out the correct set of or optimum set of hyperparameters when they are experimented on. Okay, and then for your real life scenarios, you can, like this case, you can also use multiple classification algorithms and find out which one is giving you better results. Okay, just like this case. So this is a toy example that we have worked with, and yeah, the results are pretty interesting. Thank you for listening this session today, and we will close. Thank you.